आउज़ुबिल्लाहिमिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़्दतम मिन लिसानी यफ़क़हू क़ौली रब्बि ज़िदनी इल्मा। Assalamu alaikum students, welcome to EPSEC's online support program, and this is the lecture for first year physics. The contents for today's topic are Doppler's effect, and the pages we are covering today is 286 to 291. This is the animated description of Doppler's effect. How can we define Doppler's effect? The apparent change in the frequency of sound caused by the relative motion of either the source or listener or both. So in this figure you are seeing a source, a van that is producing 800 hertz of sound, and there is an observer. If both the source and observer are at rest position, then the frequency that is emitted by the source must be equal to the frequency that is observed by the or listened by the observer if they are at a nearby distance. So the frequency of the source is independent behavior, and it does not depend upon any other change in wavelength or speed, but there must be an apparent change in the frequency that has been observed with respect to distance. So it is the very common behavior that we are dealing with daily life examples, that if I am moving away from a siren or car with horn, then I will listen less sound as compared to if I am approaching towards the car who is coming to me, or I am approaching towards the car, so I can listen the louder sound of horn or that siren. But basically the number of waves that are producing per second, this is the definition of frequency, they are same. So the conclusion of the topic is that frequency does not depend upon any other thing except the source itself, but there must be the apparent changes in frequency are observed by the relative distance between the source and the observer. So in this topic we will see some cases discussed by Doppler, and this topic is just restricted to Doppler's effect in sounds. The effect in the same behavior is observed in light as well, but this topic is about Doppler's effect in the speed of sound. The apparent change in frequency or pitch of the sound caused by the relative motion of either the source of sound or listener or both is called Doppler effect. So basically we have three cases, in which the first case in which the source of sound is moving, the other one in which the listener is moving, and the third one in which both sound source and listener they are moving. So this is known as Doppler's effect. Now we are considering a source of sound S emitting sound waves of velocity v, frequency f, and wavelength lambda. So basically these are the variables that are going to use further in the formulas. So S is the sounding source, and these sound waves are moving with velocity v, so v is the velocity of sound. Now frequency f and wavelength lambda. The distance between source S and listener is v, because the sounding source is moving towards the listener, so the distance in terms of velocity is v, Since f number of waves are compressed in distance v, so according to the velocity, frequency and wavelength relation, v is equals to f lambda, we can write lambda is equals to v upon f. Also we can write f is equals to v upon lambda. So in this case, we have to calculate the apparent change in frequency and apparent change in wavelength, and this is known as the frequency shift or Doppler shift. So the first case is the source is moving and listener is at rest. Source is moving, right, like you are seeing in this figure, that there is a source of sound that is moving towards the stationary listener. So I am showing this green arrow for the movement of source. So we know that in the initial condition the sounding source is moving with velocity v, but now if this sounding source is also moving itself, then it has the speed of a. Now this is speed of a, so we can write the formula in terms of this way. So there is the first topic, means this first case has further two parts. The part A is source moved towards a stationary listener, as you can see in this figure. Now you can see that there is a compressed behavior of wavelengths where the sounding source is moving, so the wavelength will be shrinked, and the previous behavior or the other side where the sounding source is moving away, you can see that the wavelengths or wavefronts, they are now increasing, they are now far apart. So in this case there must be a change in wavelength. So this is known as the apparent wavelength, and it is represented by lambda dash. It is v minus a. Now what is v? It is the speed of sound, and a is the speed of sounding source. So it is v minus a because the whole distance is now decreased between the stationary observer and the moving sounding source. So it is now v minus a upon f. This is your equation number 1. Now if there is any apparent change in wavelength, then there must be apparent change in frequency. So the frequency change will be f dash is equals to v upon lambda dash. Now by putting the value of lambda dash from equation number 1, it is v upon v minus a. Now this third fraction, that is f, now it is going to multiply with the whole value. So this is the final formation of Doppler's first case, in which the source is moving towards a stationary observer. So what you can see, that this is a factor v minus a in denominator. Whenever there is something that is less in denominator, the whole factor is now increased. Now I can say that f dash, the apparent frequency, apparent means that assumes to be, that observes to be, but it is not the real change. Now this apparent frequency is greater as compared to the original frequency. So now what will be the conclusion? That the observer or listener now feels that the sounding source has more sound, so the apparent frequency is greater than the original one. Now let us consider the other case, that is 1b part. So this is the source moves away from a stationary listener. Now you can see that there is an aeroplane, and this aeroplane is producing some sound waves. In the direction it is moving, the wavelengths are compressing, and on the other hand the wavelengths of sound, they are now far apart from each other. If they are now far apart from each other, and the source is moving away from this stationary observer, then the overall sound will be less. Okay, so the apparent wavelength now, because the distance is increasing, so between the observer and source, so it is now written as v plus a, where v is the speed of sound and a is the speed of that source. So lambda dash can be written as v plus a upon f. Again, there must be a apparent change in frequency, so it can be written as f dash is equals to v upon lambda dash. Now by putting the value of lambda dash, it is v plus a into f, so it is f dash is equals to v upon v plus a into f. Now again, how can you conclude the whole answer? That this is the factor v plus a, that something is greater in the denominator, then the whole factor will be less. So we can say that f dash is now less than the f. Now what is f dash? The apparent frequency now lesser than the original frequency of sound. Now question, it is the second case in which source is at rest and listener is moving. Now you can see that there is a source, stationary source. It is producing sound waves, but it is at rest. Now the observer is moving towards the stationary source. So this is again, every single case has two parts, A and B, in which one we are observing the behavior towards it, and the other one we are seeing the behavior of moving away. So it's 2A. Now listener moves towards a stationary source, so listener is moving with speed b. Okay, in the previous section we have seen that the speed of source is represented by a. Now in this case, the speed of listener is represented by b. In this case, sound waves are moving with speed v, which is v plus b. Now because the overall relative distance between the stationary source and the moving observer is now decreasing, so overall the speed can be written as v is the speed of sound plus b, so it can be written as v plus b. Now there is no change in wavelength. Okay, you can see this lambda is same as the wavelength that is approaching towards this moving observer, so there will be no change in wavelength. When we will observe the change in wavelength whenever that sounding source will move itself. Okay, otherwise if the sounding source is stationary, then it will produce the same amount of wavelength in the surroundings. So wavelength remains same, so there must be only one change, that is the apparent change in frequency. So f double dash for the variables we are using, it will become now v plus v upon lambda. Now we know that lambda has the value of v upon f. In the previous slide we have seen this relation. Now by putting the value of lambda here, we are left with f double dash is equals to v plus b upon v into f. Now how can you interpret this result, that something, this is v plus b, it is a factor that is written in numerator, now it is greater as compared to v, so the whole factor is now greater. Now we can say that this f double dash is now greater factor as compared to the f. So the conclusion is the apparent frequency is again greater than the original frequency because the listener is moving towards the stationary source. So if you have understood well about the 2A case, you can easily understand about this case in which the observer now it is moving away from the source. Now you can see that this is a sounding source and it has its own velocity 0 because it is stationary. It is producing some wavelengths, and there is an observer, it is moving in the opposite direction, means it is moving away from the sounding source. Then now the overall distance is greater between the sounding source and observer, so observer is moving away from stationary source. The observer detects fewer wavefronts per second, the frequency appears to be lower. So in this case the overall velocity is v minus b because now it is in the opposite direction, so it is v minus b, where v is the velocity of sound and b is the velocity of observer, so it is v minus b overall. The wavelength remains same because the observer is stationary, the source is stationary, so apparent frequency will be f double dash is v minus b upon lambda. Now putting the value of lambda, we have the relation of v minus b upon v into f. Now you can see that this numerator factor is smaller, so f double dash will be less than the original frequency. Now moving towards the third and the important case in which both the source and listener are moving towards each other. So it has again two parts. The 3a part is source and listener both moving towards each other. Speed of sound source is a, speed of sound is v, speed of listener or observer is b. So what we are doing here, we are just combining the first two cases and we got our result. Remember the first case in which you have seen that the f number of waves are compressing in the distance v minus a, because in this case the source and listener, they are both moving, so the wavelengths will be compressed, so the distance will decrease. Now it is v minus a, so apparent there is wavelength change because source is moving itself. Now this is lambda dash is equals to v minus a upon f, as we have written in the first case. Okay, first a case, it is similar to this first a case. Now we are also observing that now the observer or listener is also moving, so the speed of sound that is relative to listener is now v dash. Here the speed of sound is also changing because both the observer and listener and source are moving. So v dash is equals to v plus b, so the apparent frequency can be written as f dash is equals to v dash upon lambda dash, and f dash is equals to v plus b by putting the value of velocity upon lambda dash. Now in next we have to put the value of lambda dash from equation number 5. So it is the factor v plus b upon v minus a into f. Now how can we evaluate this result? This whole result in this v plus b is the greater factor in the numerator, so the overall factor is greater than 1. If it is greater than 1, then I can say that the apparent frequency is greater than the original frequency, and it is the real basic life case, because when we are moving and we are moving towards a sounding source, a car with horn, then we will observe a louder sound as compared to when we are moving away from that sounding source. Now considering the third b part, source and listener both moves away from each other, so again the speed of source is a. In this case the fewer number of waves they are approaching towards the listener, so the overall distance is maximum, so it is written as v plus a. Also when the sounding source is moving away, there must be spreading of wavelengths, so there is an apparent wavelength change. So wavelength dash is equals to v plus a upon f. Now the speed of sound relative to listener is now increasing, so its v dash is equals to v minus b because the listener is moving away. So the apparent frequency can be written as f dash is equals to v dash upon lambda dash. Now putting the value of v dash, it is v minus v upon lambda dash. Next put the value of lambda dash from equation number 6. This is the whole factor, that is v minus v upon v plus a into f. Now evaluate this factor, this is v minus b. So something in numerator that is lesser means the overall factor is now lesser than 1, so f dash is less than f. And this concludes that now if the source and listener they are moving away from each other, then the observer or listener will receive less number of wavelengths, so the apparent frequency is now lesser. There are some applications that I want to discuss with you. So this is because in the same behavior of Doppler's effect have been observed in light as well. So there is a visible region in electromagnetic spectrum. What is electromagnetic spectrum? The combinations of different wavelengths of light, and light is the behavior in which the it is basically the term of electromagnetic wave, where electromagnetic waves are those waves they do not require any material medium for their propagation, so they are of different wavelengths. The region I am talking right now is about the visible region, the colors that we are able to see in the whole universe because of this visible region in which our eyesight is lying. So there is the same behavior. If any object is moving towards you, then there must be a blue shift. Why this blue shift? Because this blue color has, if light is moving towards you, then it will turn into a blue shift. Why? Because the wavelength of blue is smaller, so there must be a distance less in the observer and the light source. So whenever the wavelengths are less, they compress to shorter wavelength, they appears to blue. If the light and the observer, they both are at rest, then it will lie into any region. But if the light is moving away from you, then this wavelength will be larger, so it will move towards the red shift, and the red color has the longer or larger wavelength in the visible spectrum. So the minimum wavelength in violet region and the maximum wavelength will lie in the red region. Okay. The next same phenomena is observed by the radar. Now what is radar? It is the abbreviation of radio, audio detection and ranging. Now these are the radio waves, and they are basically the waves that are used for detecting the position of airplane. Now if airplane is coming towards us, now the waves from radar, they reflect from plane and they move towards the smaller shift. If the frequency shift is smaller, then we observe, we understand that the plane is moving towards us. But if the wavelength shift and frequency shift is greater, then it is observed and it is understood that the plane is moving away because of their distance change. So this is all for today. You have to read this whole topic in detail from your textbooks, and I tried my best to elaborate its small itsy bitsy things. So thank you so much. Allah Hafiz.